For an example, let's do number 1. What is the net force of a 5 Newton force and an 8 Newton force acting on the object for each of the following conditions? The forces act in opposite directions, and the forces act in the same direction. So here I have an object, and an 8 Newton force acting in one direction, and a 5 Newton force acting in the opposite direction. The 5 Newton force is going to counteract some of the 8 Newton force. So the unbalanced force, the net force, would be 3 newtons in the direction of the stronger force. I used 2 sig figs because the problem gave me 2 sig figs. For B, they're acting in the same direction. So that object feels 5 newtons to the right and 8 newtons to the right. So they're going to add together. So the object would feel 13 newtons in the direction of the forces. Exercise 4, a force of 2.1 newtons is exerted on a 7-gram rifle bullet. What is the bullet's acceleration? So they gave me a force of 2.1 newtons, and I'll give it a direction. I'll just say forward. And I'm going to assume that that force would be the unbalanced force that can accelerate the bullet. They gave us the mass as 7 grams, but I turned it into SI, kilograms. That way when I plug it into Newton's second law, I will get my answer in newtons, which is SI. So here's Newton's second law, and it's written in the form where it's solved for acceleration. So all we have to do is plug in the force and the mass. We have it in newtons and kilograms, so that's in SI. And I also wrote the direction here, forward. You can think of it as another unit, and you just carry it through to the next step. So we do the math in a calculator, and we get 300. And then we still have newtons divided by a kilogram, and we still have the direction. At a glance, this looks to be 1 sig fig, but the problem was 2 sig figs. So let's find a way to write our answer in 2 sig figs. So I will use scientific notation for that. So instead of writing 300, I'll write 3 times 10 to the 2, which is 300, but then I'll say 3.0. So there's our 2 sig figs right there. And then I would like to figure out if these units, newtons per kilogram, is actually a unit of acceleration. So we'll do a unit conversion. So I take what I had to begin with and I multiply it by a conversion factor. And I'm going to convert the 1 newton into all the units that it's equal to. 1 newton is equal to 1 kilogram meter per second squared. And then the kilograms will cancel out and the newtons will cancel out. So I'll be left with 3 times 10 to the 2 meters per second squared in the forward direction. And the forward is there just because acceleration is supposed to have a direction. Exercise 10. A 75 kilogram person is standing on a scale in an elevator. What is the reading of the scale in newtons if the elevator is at rest and then moving upwards at a constant velocity of 2 meters per second? So I've got my mass of 75 kilograms and my velocity is 0. And it was implied in the problem that that velocity was constant. And if the velocity is constant, then the acceleration is 0. So here's my thought process. If the acceleration is 0, that means there cannot be any balanced forces. All the forces are balanced. And if I imagine my object, the Earth is pulling them down with the weight. They're not falling though because they're being supported from below by the scale. The scale is supporting them upwards. I suppose it might look a little weird that I drew my arrow pointing upwards right there. You could have also drawn it there. It's not a big deal. Just make sure that you realize that there's 2 forces. One is pulling down on the person and one is holding the person up. And that they have to be equal in amount, equal in magnitude, in order for the forces to be balanced. So the amount of the scale force has to be equal to the amount of the weight force, which we can find with mg. So the person's mass times g is 735. And then the units, we would gather them all up. We have a kilogram, a meter per second squared. So they all go there. But that doesn't really sound like our SI unit of force. So this is just a unit conversion then, where we could say that 1 kilogram meter per second squared is equal to 1 newton. So then we just have 735 newtons. And then, just rounding it to 2 sig figs, my final answer is that the scale reads 740 newtons. For part B, the velocity is constant, which means that the acceleration is 0. If the acceleration is 0, the forces on that object still have to balance. So the supporting force from the scale still has to balance the weight. So the scale would still read 740 newtons. For fun, I've added on an extra piece here. What would the scale read if the elevator was accelerating upwards at 2 meters per second squared? Well, in order to accelerate, there has to be an unbalanced force, and we can find that amount. The amount of unbalanced force on the person has to be equal to the mass times the acceleration. So we plug in our values, and we get 150. And for newtons, I just bundled up the kilogram meter per second squared because that's equal to a newton and just wrote N. And the unbalanced force is upwards because the acceleration is upwards. So then we can say that the upwards force has to be 150 newtons stronger than the downwards force. We had already found that the downwards force was 740 newtons. So the supporting force from the scale has to be 150 newtons bigger than that. So then the scale would read 890 newtons. So if you ever push the button on the elevator to go up, and right when the elevator is starting to move upwards, don't you feel a little bit heavier? You feel kind of squished into the floor a little bit more? It's because you're accelerating upwards. The floor of the elevator has to push into you harder in order to get you to accelerate upwards.